There is a lot of acoustic energy in various frequencies in the seawater. These may be due to the breaking waves, the mammals, and even the rain. Now, sonar equipment generate acoustics in quite a structured and distinct pattern. A task of a surveyor and the survey tech and even the processors and the geologist on the job is to distinguish between the signal and the noise. Now the technology comes in its aid. Nowadays we have got the face matching technique and the coding techniques of the signal that make the signal uniquely identifiable. On a decibel scale, everything refers to power, which basically is amplitude squared. To put it in perspective, 0 decibels correspond to the normal threshold of human hearing, while 130 decibels is a point where sound becomes painful for the human ear. Now because it is amplitude squared, 10 dB is 10 times increase in the signal, while 20 dB is 100 times increase, and likewise 30 dB is 1000 times increase in the signal level. As a rule of thumb, an increase of 3 decibels doubles the sound level. Usually a higher decibels represent better signal performance, except in the system like the CHIRP. Our CHIRP system provides a high range and high resolution using not a single frequency but a banquet of frequencies, also called as sweep frequencies. So while in the usual continuous wave systems, it is the pulse length that matters, but in the CHIRP system, it is the bandwidth that matters. Now, unlike the radio waves in air, the sound waves or the acoustic wave suffer much less attenuation, but the sound energy suffers loss due to spreading and absorption. The absorption is due to the loss of acoustic energy to the heat while being propagated. So we can say that absorption is just the attenuation caused by the change in medium in the water. Now absorption increases with increase in frequency and salinity, but it also increases with decrease in temperature and the hydrostatic pressure. So it is inversely proportional to temperature and the hydrostatic pressure. Let's take for instance a resonator multibeam system with a high frequency of 455 kHz. Now on its ocean menu, the range setting which is available allows us to alter from 0 to 120 decibels per kilometer. Now in case the exact absorption values in that area for that frequency are not known, which will be the case most of the times, a value of 110 decibels per kilometer for salt water and 70 decibels per kilometer for fresh water is quite recommendable. While in a corresponding similar system in the Gulf water, it had been quite alright with 80 decibels per kilometer. The bottom absorption values not only vary with frequency but also with the bottom type, the seabed type and the grazing angle. The losses of absorption increases with the increase in frequency and its grazing angle. Now let's take an instance of 24 kHz system with a grazing angle of 15 degree. The approximate absorption value on a rocky seabed surface would be around 20 dB meter square, while on a sandy seabed surface it would be around 30 decibels meter square, and on a muddy surface it would be as high as 40 decibels meter square. Now about spreading losses, it is basically because the total amount of energy remains the same while the wave spreads out of the source. Pressure is isotropic. As the wave is spreading with time and distance, energy per unit length of the wave is getting diminished. The intensity falls off for the square of the distance. So as a rule of thumb, 6 decibels diminishing of the sonar energy would be there for each doubling of the distance. For a resonance system, out of the ocean menu setting available of 0 to 60 decibels, it is recommended to begin in the middle with 30 decibels.